Happy Thursday. Today we are going to be doing acid-base chemistry and more solution chemistry. So just so that you know where we are, we have acid-base chemistry and then equilibrium, and then next weekend you guys have your last quiz for the semester, and then before you know it, you guys have a final, and then um, the semester will be over. I'll give you more information about your final probably next week when I've had time to catch up, and hopefully you guys will be able to muster through the home stretch here. So let me just make sure that you guys are, make sure that I have my screen on. Okay. So what you are seeing is my computer, and I've been trying to get my PowerPoint onto my iPad, but it seems not to work. So I probably need to talk over using my computer, but it's still pretty good. I can just use the writing tools. Anyway, I think we left off, unless you guys have any questions. Let me just double check real quick. Okay. For those of you in lab, today we are going to be doing solution chemistry. So hopefully you remember what we talked about on Tuesday, because a lot of the calculations for that lab is based on Tuesday's discussion. But let me go ahead and get started on acid-base chemistry, because we do have a lot to talk about. And got to remember that when we talk about acid-base chemistry, it's about the chemistry. It's about a chemical that wants to give off its hydrogen. Whenever it does that, then it has characteristics of determining the hydronium ion concentration. So that's what we're going to be looking at today. I think we left off last time talking about, let me just double checking. We talked about strong acids and strong base. So I want to show you this movie real quick so that you guys can get a sense of what a strong acid is. No, the quiz is going to be next weekend. Okay. So if you take a look at the regular schedule, we have acid-base chemistry, and then equilibrium, and then we have the quiz. So it's not this weekend. So let's take a look at this movie real quick, and then make sure that the audio is okay.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms hydrochloric acid. Hydrogen chloride is very soluble in water and is completely dissociated. It is therefore a strong electrolyte. Nitric acid is another common strong acid. Upon dissolving in water, nitric acid completely ionizes to form an acidic.
You guys able to hear that? I think there was something in the discussion in the chat saying you couldn't or you could. No, I was pressing to try and okay, you can't hear it. Okay, let's do this over again. Okay. Oops.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms hydrochloric acid. Hydrogen chloride is very soluble in water and is completely dissociated. It is therefore a strong electrolyte. Nitric acid is another common strong acid. Upon dissolving in water, nitric acid completely ionizes to form an acidic solution. Like hydrogen chloride, nitric acid is a strong electrolyte. Acetic acid is the major ingredient of vinegar. When acetic acid is added to water, it is not completely ionized. It is therefore termed a weak electrolyte or weak acid.
So hopefully, what you got out of that little clip was that there's two classifications of acid. One is a strong acid, and those are when you put it in water, they completely break apart to their ions, H plus and the anion, and they do that at 100%. And last time I told you that there were seven of these. On the other hand, weak acids, and that would mean the entire acids that are not in these seven. That's sort of a generalization because there's actually more strong acids, but for your purpose, just remember the seven. But if it's not that's those seven, then in general, especially for your class, then it's considered weak. And hopefully you saw in the movie, acetic acid is one of those. In fact, next week you guys are going to be titrating acetic acid. But if left on its own, when you put it in water, the hydrogen only comes out a partial percent of the time. Now you can get the hydrogen off 100% of the time if you react it with a strong base or with a base, then you run the show. But if you just put it in water, that's the nature of acid. They break apart and form hydrogen plus the hydronium ion and the anion. And that's the same thing with a base. A base will generate hydroxide ion and whatever the counterpart is. So think of strong not necessarily as concentration, but strong in terms of the chemistry. And if you mix those two, then you're going to be in trouble because what will end up happening is there's usually a question that says, okay, among these, and I'll give you concentrations with weak acids, among these, which are the strong acids? And it all has to do with the chemistry. It has nothing to do with concentration. If I ask you which is the most concentrated acid, then you're looking at the most moles per unit volume. Okay, so that's what I want you to get out of that. It's a very fundamental concept because you guys are going to see it in stoic in Chem 200, but more so in Chem 201. So after seeing that, then we look at strong bases, and strong bases again are basically chemicals that will, when you put it in water, dissolves, okay, and they have a hydroxide in them. And when they do that, then if you put, say, a 1 molar sodium hydroxide solution, then you get a 1 molar hydroxide ion. So if you take this chemical right here, and this is a strong base, this one right here, and you put it in water, and you've got a, say, 1 molar, because we're dealing with solution chemistry, then when it dissociates, it's going to give you a 1 molar sodium ion and also a 1 molar hydroxide ion. And you might ask yourself, how can 1 molar sodium hydroxide give you 1 plus 1 molar, 2 molar ions? Well, that's because the sodium hydroxide breaks up into two parts. So it gives you equal concentration of the sodium and the hydroxide. Okay? Pay close attention to chemicals like these because a 1 molar calcium hydroxide will give you 1 molar calcium, but 2 molar hydroxide. Okay? So you have to pay attention to the formula. In fact, in my 201 course, we there's like a couple of chapters devoted to just acid-base chemistry, and I just gave a problem where we're doing a titration, and the chemical that you're titrating with, the chemical in which you're adding is calcium hydroxide. A lot of my students in Chem 201 just sort of assume that 1 molar calcium hydroxide will give you 1 molar hydroxide. Don't make that mistake. You have to look at the formula. You have to realize that for every 1 calcium hydroxide, you get 2 hydroxide. Okay, so that's strong base. Other ways, other bases are going to be one in which a chemical will react with water, and when that occurs, what happens here is that there's a lone pair on that nitrogen, and so the water will give up its hydrogen. Okay, it's going to give up its hydrogen and just break that bond right there, because water is sort of acidic, and it's going to latch on to form NH4 plus and hydroxide. So that's where you get your hydroxide to make the solution basic. Okay, when you have more hydroxide in your solution than hydrogen ions or hydronium, then the solution is basic. When you have more hydrogen ions or hydronium than hydroxide, then the solution is acidic. You will always have a certain amount of hydronium and hydroxide, and it's balanced when it's neutral. When it's neutral, you have equal amount of hydronium, H3O plus, and hydroxide. When it's acidic, you have more hydronium, H3O plus. When it's basic, you have more hydroxide. And you'll see that when we get further into this chapter. Okay, so again, you generate hydroxide either by generating hydroxide as the chemical dissociate or reacting with water. And here's a second example in which the carbonate reacts with water to form bicarbonate. This chemical is called bicarbonate. And then you also get hydroxide. You notice that the hydrogen in water is what is donated to that carbonate ion. And so what's left over is the hydroxide. You know, if you have a basic solution, because the product are generally going to be hydroxide. You know you have an acidic solution because the product is going to be hydronium. The dominant species in the solution is going to dictate whether it's acidic or basic. And then you measure acidity and basicity based on the pH reading. And you guys probably have heard of that. If you have an aquarium or fish aquarium and you're going to test for the acidity level, then you use a test paper that sort of gives you an idea of what the pH of that solution is. And again, we will be looking at that in more details in this particular section. So let's take a look at this real quick, this movie.
Bases are substances that increase the concentration of hydroxide ion in water. Water-soluble ionic hydroxides, such as sodium hydroxide, potassium hydroxide, and calcium hydroxide, are among the most common bases. When sodium hydroxide is dissolved in water, it completely dissociates into sodium and hydroxide ions. Because sodium hydroxide is completely ionized in solution, it is referred to as a strong base. It is also, of course, a strong electrolyte. Ammonia does not contain the hydroxide ion, but is basic in water. When gaseous ammonia dissolves in water, it reacts with water to form the ammonium and hydroxide ions. However, ammonia is a weak base. The equilibrium forming the hydroxide and ammonium ions lies largely to the left. At any given time, most of the ammonia is in a non-ionized form.
So again, you see the illustration of what makes something strong or weak. Strong generally means that it breaks apart 100% of the time. Weak tells you it's only a partial percent of the time. It applies to both acids and base. So Um, we left off last time talking about a new definition called a Lowry-Bronsted. And so instead of discussing acids and base in terms of increasing H plus and OH minus, we now define it in terms of a chemical donating a proton. And remember, a proton is nothing more than a hydrogen atom with its electron stripped off. Because a hydrogen atom is one proton in the nucleus, no neutrons, and one electron. That's why it has a mass of one. If you have a different isotope like deuterium, it's got one proton and one neutron. But we're talking about just the hydrogen atom and with one proton and one electron. When that electron is stripped off, what you have is one proton left over. And that's why we use the notation H plus, because that's the chemical that generally is going to be involved in the chemistry. Now, of course, H plus is too reactive. A proton's too reactive. It's not going to exist in water. What it will do is stabilize itself and find a lone pair. And it finds a lone pair in the most abundant chemical in the aqueous solution. And that abundant chemical is water. And so whenever you generate H plus, you actually are going to form H3O plus, because that H plus, that proton, is too reactive. It needs to stabilize itself, and it latches onto the a water molecule. And now the water molecule is called a hydronium. On the other hand, a base is going to have a lone pair. And so any chemical that can deliver a hydrogen is going to deliver it to the base. And so that's why we define a base as a proton acceptor. Okay. And a chemical reaction would involve a chemical that wants the hydrogen and a chemical that wants to give off the hydrogen. Okay. So an example of that is hydrochloric acid and ammonia. When you put hydrochloric acid and ammonia together, hydrochloric acid, HCl, has a strong affinity to get rid of its hydrogen. On the other hand, ammonia is a base. And so what will occur is that that hydrogen on hydrochloric acid will latch on to the lone pair. You got to have a lone pair on the chemical on the base, otherwise there's nothing to latch onto. Okay, that's a motif that a base needs to have. It's got to have a lone pair. That's why we paid attention to Lewis structure, so that the hydrogen ion can be attracted to it. Once they are attracted to it, then we have a new formula called NH4 plus, and then the chemical that is missing the hydrogen becomes Cl minus. What we're going to be talking about next is something called conjugate pairs. Conjugate pairs are chemicals that differ only by a hydrogen. So in as a preview, let me just change my pen here. These two are conjugate pairs. And the reason why they're conjugate pairs is because they only differ by hydrogen. These two are conjugate pairs. Again, the reason why they're conjugate pairs is because they differ by a hydrogen. And we'll talk more about these in the next few slides. In acid-base chemistry, when you have a hydronium ion and hydroxide ions like you see down here, the neutralization reaction generates water. Okay, because you have a hydrogen ion here and a hydroxide ion here to form H2O. And then the remaining chemical is the salt, the ionic substance. So let's take a look at this. Going back to that example, you see how NH3 becomes NH4 plus. That's why you see that arrow. HCl, by giving up its hydrogen, becomes Cl minus. Well, like I said, these are conjugate pairs. The conjugate pairs always differ by a hydrogen. Now, whereas ammonia is a base in the forward direction, how do you know it's a base? It's the chemical that accepts the hydrogen Okay. Ammonium, remember, ammonia is NH3. Ammonium, IUM, is NH4 plus. In the reverse direction, however, ammonium is the acid, because if you go in the reverse direction, it's NH4 that will deliver its hydrogen to the chloride, and so that's the proton donor, and then the chloride will be the proton acceptor. So in one direction, NH3 is the base, HCl is the acid. In the other direction, NH4 plus is the acid, Cl minus is the base. When you have conjugate pairs, one will always be an acid, another will always be the base. So you could recognize them because the acid generally will have more hydrogen than its base counterpart. So NH3, that's a base one, and NH4, that's the conjugate acid. HCl is the acid 2, and Cl minus is the conjugate base. Again, conjugates always differ by a hydrogen. Here's another example. We have bicarbonate now, HCO3 minus. In water, it can deliver its hydrogen, right here. And by delivering its hydrogen to water, it's the acid. But in the reverse direction, H3O plus is the one that delivers its hydrogen to the carbonate ion. Remember, this chemical is called bicarbonate. Okay. And this chemical is called carbonate. So in the reverse direction, the carbonate is the base and the hydronium is the acid. The conjugate pairs is water and hydronium. And the other conjugate pair is bicarbonate and carbonate. You guys should be able to recognize which are the conjugate pairs, and between the conjugate pairs, which is the acid and which is the base. And it's not difficult, okay? But the reason why we talk about these is because what you will find out is that when you have a fairly strong acid, its conjugate becomes a base, but a very weak base, okay? It becomes the anti-original chemical. So let's move on. Here are more examples of conjugate, and you could probably just go through here and pick the conjugate pairs, and it's not difficult to do that because they always differ by only one hydrogen, okay? They differ only by one hydrogen. So make sure you review Chapter 7. Chapter 7, remember, is balancing chemical equations. We do a lot of acid-base chemistry reactions, and so you should remember not only how to balance it, but also know the name and the formula for some of these acids, like nitric acid or hydrofluoric acid or acetic acid. So again, in a neutralization reaction, you generally have an acid right here and a base, and you form water and the salt. And these are just examples. So one of the things that you saw back in chapter 13, solution chemistry, was that when you have a chemical reaction between an acid and a base, then it's called a neutralization reaction. But the reason why it's important is because in a acid-base chemical reaction, you can usually do an analysis. Usually you have a chemical, you have a solution that you want to analyze. And suppose you want to figure out exactly what how much of the acid do you have, or what is the concentration of the acid that you have. Then the way you would do that is through a titration process. This will jumpstart you guys for next week's lab. In next week's lab, you guys are going to take a solution of vinegar. Vinegar has a certain concentration of acid in it. What you guys are going to do is take a certain volume of vinegar, and then you're going to add an acid to it. But you're going to deliver the acid in such a way that you can measure the volume. And if you measure the volume and you know the concentration of that base that you are adding, then you can figure out how much moles of base to deliver when the solution is completely neutral. And the solution's completely neutral at the equivalent point. And that's because the hydrogen ion concentration and the hydroxide ion concentration are equal. So when that happens, it's called the equivalence point. When you do an experiment and you stop the experiment, it's called the end point. You do the experiment so that the end point matches the equivalent point. But the equivalent point is the terminology we use in chemistry to indicate that the moles of the acid equals the moles of the base. The endpoint is a terminology we use in an experimental procedure to indicate stop the titration. We now think we have the moles of the acid equals the moles of the base based on visualization, usually an indicator, that we've reached that point. Okay, so this is what usually you do in a titration is you deliver a precise amount of um, analate. The chemical that you're doing the analysis on is called the analate. And here, what you are seeing is we're taking an aliquot. An aliquot is a portion. And we're delivering 20 mils of this acid to be analyzed. And remember that the chemical that's being analyzed is called an analate. And the chemical that you are delivering to analyze that is generally in a burette. And this chemical is called the titrant, because that's the chemical in which you are going to be titrating. So it's called the titrant. So the chemical to be analyzed, whether it be an acid and a base or a base, is called the analate. The other chemical that you are going to be analyzing with, the titrant, has got to be the opposite. You cannot analyze an acid with an acid. You can analyze an acid with a base, you can analyze a base with an acid, but not the same. Because what you need to do is you need to get to the point where you've added enough of the titrant so that the moles of that chemical is equal to the moles of the chemical that you're analyzing. That would be the equivalent point. And how do you know you've reached that point? Because generally what you will do is add another chemical, just a few drops, called an indicator. And that indicator changes color when you've reached that point, when you've reached the equivalence point. And that's what you see right here in this illustration. Okay, indicator changes color at the endpoint, and you assume that the endpoint is the equivalent point when you're doing your experiment, and that's when the moles of the titrant, the moles of the acid equals the moles of the or the moles of the base, because the base generally is the titrant, is equal to the moles of the analate, and generally the analate is the acid. So this is how you do the titration. You have an analyte here, let's say that's an acid, and you've got a base here, the ones in OH, and you keep adding. And you notice that when you add hydroxide, it neutralizes and forms water. And so what happens is that the hydrogen ion in your solution becomes lower and lower in concentration. As it becomes lower and lower in concentration, then the solution becomes less acidic. And we use pH. pH means the power of hydrogen to indicate acidity. So as we add more and more base, the pH will go from a low level like pH 1 to a higher level. Okay, it'll go from pH 1, pH 2, pH 3. Now, when we reach the equivalence point for a strong base and a strong acid, there is neither excess acid or base in the solution anymore. And when that happens, then we have a pH of 7. Okay, and at that point, the indicator changes color. And so that's what you see right here. Now, if you add more base, now the solution becomes more dominant in the hydroxide, and the solution will now have a pH greater than 7, telling you that the solution is now becoming more basic. So that's what happens during a titration problem. Let's see a movie illustrating this real quick. Okay. Oops.
Quantitative addition of a solution of known concentration to one of unknown concentration, resulting in a chemical reaction, is called titration. Acid-base titrations are among the most common. When a standard sodium hydroxide solution is added to a hydrochloric acid solution, the neutralization reaction occurs. A pH meter is employed to measure the acidity of the solution. To illustrate, let's add 0.100 molar base to precisely 50 milliliters of a 0.100 molar acid solution. The pH increases slowly at first. As the amount of base added approaches that required for complete neutralization, that is the stoichiometrically equivalent amount, the pH begins to increase more rapidly. The last few drops of added base change the pH from about 3 to 7. The pH is 7 when precisely 50 milliliters of base have been added. We are then at the equivalence point, or end point, at which the stoichiometric amount of base required to neutralize the acid has been added. Addition of 1 drop of NaOH beyond that needed to neutralize the acid causes the pH to increase from 7 to about 10. Thus, the endpoint of the titration can be determined with high precision.
So that's your experiment next week, actually. You guys are going to be doing a titration. And again, you guys are going to be analyzing vinegar, and you will be able to calculate the concentration of vinegar based on your titration. Well, you guys aren't going to be doing the experiment. You're going to be watching the experiment. And hopefully this COVID-19 will be over, because one of the fundamental things that you guys need to learn in any chemistry course, if you haven't done so already in high school, is a titration. Titrations are so popular, they even have titration competition in the Science Olympiad. But you guys can have it. If you ever get into Chem 200 and it's not a virtual lab, then you guys will be doing a whole bunch of titration. Anyway, again, the idea is that how do you know when to stop? You know when to stop, okay, because the indicator will change color. And here you have different indicators, and these are the different color range. The most common indicator that you will use is going to be phenolphthalein. And phenolphthalein goes from colorless, that's what you see right here, okay, to a pink color. And it actually changes color above pH 7. But the inflection point is so steep that 1 drop will cause that solution to go from a pH 4 all the way to about a pH 9. So that solution will turn pink just on 1 drop. And generally, the critical information that you need in a titration is how much of the titrant did you add. If you just add 1 drop and you stop, you have a pretty good idea of the exact volume that you added to the analate, so that now the volume and the concentration, now you remember this from the previous chapter, the volume and the concentration gives you the moles. So that's what you are doing in a titration. You're trying to figure out the moles of the titrant that you are adding based on the volume you delivered and the concentration of the titrant that you are adding. So when you reach the equivalence point, it just takes 1 drop to change that color. You stop right there and you have pretty much a very good idea of the exact volume by which you've reached the equivalence point. That would be called the endpoint. Here's the chemistry of what happens. Okay, this is the chemistry of what happens. Phenolphthalein is this chemical right here. Notice that this is a carbon. This is a carbon right here in the center. Show you that. That's a carbon right there. And you notice it's got 4 bonds. That means that that carbon's tetrahedral. When the chemical has an arrangement where those bonds are arranged in a tetrahedral fashion, then the chemical is colorless. But when there are no more hydrogen ions in your solution, okay, because it's all been neutralized by the hydroxide, so you've reached the equivalent point, and the hydronium and the hydroxide are equal, then the next hydroxide, the next molecule of hydroxide, won't have any hydronium to attack. And instead, what happens is that there is a hydrogen in this chemical, it's over here, that reacts with the hydroxide, and then this chemical will convert over to this configuration, and then it changes color on you. But it doesn't react with the hydroxide as long as there are excess hydrogen ions in the analate. But once all the hydrogen ions have been consumed because you reach the endpoint or the equivalent point, then the molecules of hydroxide that are in excess now will find the indicator. The indicator will react with the hydroxide because it's going to be a weaker acid, essentially. And now the configuration changes and you start to see that solution turning pink. That's the chemistry of why you see a color change when you reach the equivalent point. And you're actually a molecule or 2 past the equivalence point, because the equivalence point would be when the hydrogen ion and the hydroxide ions are equal. But when they're equal, the phenolphthalein is still going to stay on that configuration. You need a few more molecules of hydroxide in excess so that the phenolphthalein molecule can now deliver its hydrogen and change configuration. But the amount of hydroxide is so minute, we can make that assumption that the volume we delivered is the equivalent volume. Okay, so that basically is the chemistry of acid-base titration. And this again is a titration curve right here that you see, and it's that 1 drop takes it all the way from pH 4 all the way to pH 10. And even though below pH 7, phenolphthalein doesn't change color, the pH just changes dramatically with that 1 drop all the way to 10, that it does change the color of the solution. So when you guys do a titration problem and you stop adding your titrant, then you know you've reached the stoichiometric equivalence. Okay, acid-base titration is nothing more than a stoichiometry problem. If you look at this problem, we won't solve it, but I just want to familiarize you with the language we use in a titration. It says a titration is used to determine the concentration of HCl. That means HCl is your titrant, okay? Because a titration is used to determine the concentration. You're analyzing HCl. Exactly 20 milliliters of the acid. So in here, you have 20 milliliters of that analate is placed in a flask with phenolphthalein added. All you need is 1 or 2 drops. Now, 1 or 2 drops are millions and billions of molecules, and so that will be sufficient so that when you are a drop or two, or even a few hundred molecules above the equivalence point, those phenolphthalein molecules will change color on you. So um, phenolphthalein added. Now this right here is the titrant. This is the information on the titrant. You've got a concentration, you've got a volume. So initially, what you have is you read the initial volume here. So you have a volume initial. And generally, that volume initial will be like 0.02 milliliters. And you might ask yourself, why is my initial volume 0.02 milliliters when there is more than 50 milliliters of titrant in that burette? Remember, we are going to measure how much is delivered. And so we're reading the initial volume of 0.02, and then when we stop, we're going to read that final volume as 18.36. The difference between 18.36 and 0.02 is 18.34. That's the volume that is delivered. It's not important to say that, oh, I have 50 milliliters here, and so I should read 50 milliliters. No, that's not what a burette is meant for. It's not to deliver a precise volume. It's to deliver a measured volume. So you have to be able to read the initial and the final, and then you take the difference to figure out exactly the volume you've delivered to the analate. Okay, and make sure you remember that burettes are read to the 100th of a milliliter. They are that precise, 2 decimal place over. So that's what this problem is. You've got 0.0982 moles per liter. You're delivering 18.34 milliliters. You can calculate the moles right here. This will be the moles of hydroxide. And if you divide by remember that the moles of hydroxide is equal to the moles of the acid. And if you divide by the volume of that acid, you now know the concentration of your analate. So what I'm doing here is I'm basically using a stoichiometry problem. You have the moles of the base, that's the concentration times the volume, and you're using the stoichiometric ratio. It's a 1-to-1 ratio. It's a 1-to-1 ratio. 1 mole of hydroxide equals 1 mole of acid. And then I'm just taking that mole of acid, dividing by the volume of that acid, and now I have the concentration. So if you look at the last problem that we did in chapter 13, it's exactly the same thing. Okay, it's exactly the same thing. Here's another problem. We've got 100 milliliters of 6.8 times 10 to the minus 3 molar hydronitric acid is titrated with sodium hydroxide. What volume of 0.0010 molar sodium hydroxide is necessary to neutralize this reaction? Remember that sodium hydroxide is monobasic. If I gave you calcium hydroxide, then you got to realize that the balance equation is 2 calcium hydroxide for every, 2 acids for every 1 calcium hydroxide. That's the balance equation. So first take care of the fact that this is a stoichiometry problem, and that for this present problem right here, it's a 1-to-1 ratio. If the base was calcium hydroxide, it's a 1-to-2 ratio. But going back to this problem, we can see that this will give us the moles of an acid. And if we now have the moles of the acid, which is equal to the moles of the base, then when we use this concentration right here, we can calculate the volume. And that, again, we have the acid. This will be the acid right here. Let me just show you that this is a stoichiometry problem. We have the volume, we have the concentration, we can calculate the moles of the acid. We know that the moles of the acid equals the moles of the base. So to get the volume, we can use the concentration that was provided. Together with the moles, we can get the volume. It's the same thing that we studied in chapter 13. It's just an extension. Okay, it's just an extension. And actually, this was the same problem that we did in chapter 13. This was the exact same problem. Comes out to 680 milliliters. But now you know the context of that solution chemistry problem. It's in the context of acid base. Remember that a strong acid is a chemical that will dissociate completely, so it's a strong electrolyte. A weak acid is a chemical that does not dissociate completely. It's a weak electrolyte. Electrolyte has its origins in terms of conduction of electricity. When you have a chemical that spews off all its ions in the water, then it's going to be a great conductor of electricity. When you run electricity through here, because this is such a great conductor, you get a very strong luminescence of the light bulb. On the other hand, if you do the same setup, but you have a weak electrolyte, what you have is you have a limited capacity to transfer the electrons and completing that circuit, because you only have few ions to transfer the charge. You're going to have a weak intensity of that light bulb. And that's generally, in the old days, how we determine whether we have a strong electrolyte or a weak electrolyte. But these days we know whether the chemical will break up 100% or less than 100%. And then if it doesn't break up at all, then this light bulb will not even light, okay? It would not turn on, because this is an open circuit right here. You see that? And the electrons will go here and then stop, because what happens is that there is no there's no way for the negative charge to continue on to the other poles. With a strong electrolyte, the ions will deliver that negative charge to the other poles, and then the ions will deliver its electrons, and then the electrons go on, and you have a very strong intensity, because you've got a very efficient way of the electrons going through the wire. Here, with a weak electrolyte, you don't have very good efficiency. You get poor luminescence, and then for a non-electrolyte, you don't get any luminescence at all, because you can't. It's an open circuit, basically. It's not a closed circuit. So, what are some of the chemicals that are weak electrolytes? Well, weak acids or weak base. And the way we determine the efficiency of a chemical to deliver its hydrogen is through a value called Ka. Ka is an indicator of how well it dissociates, how well it ionizes, how well it splits up. Ka is never negative, but it can be very small, 10 to the minus 8, for example. That's 7 zeros preceding a 1, okay? That's a very small number. Ka can be also very big. It could be something like 10 to the 7th, okay, or 10 to the 3rd. Whenever you have Ka that are big, then that means that the chemical will easily break apart. Ka is called the dissociation constant. This is called a dissociation. Remember that acids will break apart. When they break apart, we call it a dissociation. DISS, well, if I had a pen, dissociation, DISCOIATION. Okay, that's the dissociation. And it's called a dissociation constant because for that chemical will always have that constant at a certain temperature, and it tells you the efficiency. Okay, so let's take a look at some of the dissociation constant for these are all weak acids. And how do you know they're weak acids? It's not any of our top 7. None of these made it to our top 7 strong acids, so therefore they must be weak. Look at their value: 6.8 times 10 to the minus 4, 4.5 times 10 to the minus 4, 1.8 times 10 to the minus 5, 3.0 times 10 to the minus 8. So the further down we go here, the smaller these values are. So what this chart is telling you is that as we go down this table, we have weaker and weaker acids. These things will have less efficiency to get rid of its hydrogen. Whereas the chemicals on top, even though they are weak acid, remember, because they don't deliver their hydrogens 100% of the time, they are at least the strongest among the weak. Okay, let me say that again. Because their Kas are bigger than the ones down here, among the weak acid, these chemicals up here are the strongest among the weak. These chemicals down here are the weakest among the weak. And we use these values, these Kas, as a way to indicate their weakness or their strongness in terms of getting rid of their hydrogen. Okay, so these are weak acids down here. These are weak but fairly strong weak acids up here relative to making that comparison. Some chemicals can deliver more than one hydrogen, like ascorbic acid. That's your vitamin C. Okay, that has 2 hydrogens to deliver. Carbonic acid, that's the acid in your beverage, soda beverage. Okay, it's got 2 hydrogens to deliver. Oxalic acid has 2 hydrogens to deliver. Phosphoric acid has 3 hydrogens to deliver. Therefore, you have the first hydrogen coming off, it has a Ka. Remember what I said? Ka is an indicator of efficiency. The smaller that number, the more, the less efficient it's going to get rid of its hydrogen. But then the hydrogen is going to come off for the second hydrogen is also going to come off because these chemicals are called polyprotic, meaning many protons. So polyproducts have more than one hydrogen to deliver, and they're going to have a second Kas. And the second Ka tells you the efficiency of getting rid of that second hydrogen. The second Ka are always going to be less than the first. Okay, the second Ka is always going to be less than the first. Why? Because the first, you're getting rid of the hydrogen from a neutral species. The second, you're now getting rid of the hydrogen from a negative species. It's much more difficult to remove an H plus from a chemical that's already a negative charge. You're going to have to work at it. So that's what you see right here. Okay, what you see is that these values over here are going to be much smaller than the first. The first are going to come off not very efficiently, but the second's even going to be worse in terms of coming off. And then for some of these, you're going to have a third Kas. So depending on how many hydrogens a chemical can deliver, you have a Ka1, Ka2, or Ka3. I've never seen a chemical with a Ka4. Okay, these things are called polyprotic, because they can deliver multiple hydrogens. Look at phosphoric acid. The first one comes off at 10 to the minus 3. The second one comes off at 10 to the minus 8. The last one comes off at 10 to the minus 13. Much more inefficient in trying to get rid of that hydrogen. And this is by putting it in water. Now, if you can force phosphoric acid to get rid of its hydrogen, you can do so. And the way you do so is you put a very strong base in there. If you put a very strong base with phosphoric acid, the strong base will tell phosphoric acid, give me all your hydrogens. Okay, like if you mix phosphoric acid with sodium hydroxide, if you have an equal amount of phosphoric acid and sodium hydroxide, then only the first hydrogen will come out. But if you have 3 times more sodium hydroxide than phosphoric acid, then the sodium hydroxide will pull off 1, 2, and 3 hydrogens of that one phosphoric acid, because there are 3 times as many sodium hydroxide. The strong chemical will always run the show. It'll demand the weak chemical to be obedient. Okay? It'll demand, if you have a weak base and you put in a strong acid, the strong acid will say, here, take my hydrogens, even though how weak you are, you're going to have to take it. If you have a weak acid and you put in a strong base, the strong base will say, give me all your hydrogens, even though you don't want to get rid of it. It's going to demand those hydrogens because the strong chemical, whether it be an acid or a base, is running the show. What exactly is a Ka? Let me get out of here real quick. The reason why I want to get out of here is because this right here is not formatted correctly. Okay, let me go back. So whenever an acid is in water, okay, remember, whenever an acid is in water, like this, then what will happen is that the chemical, because it's an acid, will react with water and it will deliver its hydrogen to that water. Because it's an acid, its job is to be a proton donor. It's going to deliver its hydrogen to the lone pair on water. Remember, water has 2 lone pairs, and you get hydronium ion, and then what's remaining is the conjugate of that acid, A minus. But we can write an expression. It's called a mass action expression. And that mass action expression is the products, it's what we see right here, over the reactant. Okay, the concentration of the products over the concentration of the reactant. Now, it's too bad that we don't cover equilibrium first. We cover acid-base chemistry first, because if we had covered equilibrium first, then this will be well explained. But for now, just kind of take the fact that if we write the products over the reactant, then this ratio right here, no matter what concentration of acid you have, will always be equal to a constant value. And that constant value is called the equilibrium constant, or the dissociation constant for K, for acids. We call it Ka. A here stands for acid. Okay, the K stands for equilibrium constant. But what I want to explain here is that this constant tells you the ratio of the products over the reactant. So if the product is greater than the reactant, then this ratio is going to be greater than 1. Okay? Because if we have 10 over 1, isn't 10 over 1 greater than 1? On the other hand, if we have 1 over 10, then that 1 over 10 is less than 1, or 0.1 in this particular case. So Ka tells you in this mixture right here, because all these are sitting in the same solution, in this mixture right here, which are the dominant species. When Ka is bigger than 1, it tells you that the product is going to be the dominant in that mixture. And the only way it's dominant is when that acid dissociates 100%. If, however, it doesn't dissociate 100%, then the reactant will be the dominant species. And so that ratio is going to be less than 1. And that's what happens for all the weak acids. You have a Ka that is 10 to the minus 4, 10 to the minus 8. It basically tells you that 10 to the minus 4 tells you that the reactant is about 1,000, 10,000 times more concentrated. This is more concentrated when it's 10 to the 8th than these chemicals right here. So the math, and this is so true when you guys get to Chem 200, the math is telling you the same thing in terms of the concept. Okay? When you have a weak acid, the dominant species is going to be the reactant. The Ka will also tell you that the dominant species is that, because that value right here is going to be less than 1. The concept tells you for a strong acid, this chemical right here, the product, is going to be the dominant species, because it's going to uh, it's going to be such that the chemical are going to dissociate. When the product is the dominant species, then the numerator is going to be bigger than the denominator, and then that Ka is going to be greater than 1. So like I said, the Ka is an indicator of efficiency. If it's greater than 1, basically it's telling you it favors the product side. If it's less than 1, it's going to favor the reactant side. Depending on how small that Ka value is, it's going to tell you how inefficient the reaction is in forming the products. So large Ka, much bigger than 1, the equilibrium, that's what this double arrow means. Equilibrium just tells you that when the reaction seems to stop and the chemicals are at their stable state, which of these chemicals are going to be the dominant species in solution? That's what I'm saying. The equilibrium lies very far to the right. Very far to the right means that the product dominates. When Ka is much less than 1, then the equilibrium lies very far to the left. The reactant are the dominant species. Okay? So, rehash, strong acids are going to have very large Kas. In fact, they have so large of Ka, you won't be able to find them. You just assume that it's 100% dissociation. Don't look for a Ka for these strong acids. You're not going to find any, okay? Because it's assumed that these things will just break apart into their hydronium and their anion 100% of the time. So if you've got 0.5 molar HCl, okay, that's the concentration you have. When it goes into water, you're going to have 0.5 molar hydrogen ion and 0.5 molar chloride ions. When you have 1.02 times 10 to the minus 3 nitric acid, guess what? You're going to have 1.02 times 10 to the minus 3 hydrogen ions. The concentration of the original acid is going to be equal to the concentration of the hydrogen ion. But that's not true for weak acids. All these are weak acids because it's not in our top 7. So when you have 0.5 molar carbonic acid, that's carbonic acid, your hydrogen ion is going to be much, much less than 0.5 molar because not all the carbonic acid will generate hydrogen ions. It's a weak acid. The way you calculate the hydronium ions is through equilibrium, which we are not prepared to do in this class uh, at this point. You guys will see that in Chem 201. But just know that if you have a weak acid, your concentration is going to be much, much less than the original concentration of that acid. Okay? Here's nitrous acid. Don't confuse nitrous acid with nitric acid. Nitric acid is HNO3. Nitrous acid is HNO2. This is the nitrate ion. This is the nitrite ion. Okay, NO2 minus. Anyway, if you put this in water, the concentration of your hydrogen ion is going to be much, much less than 1.05 times 10 to the minus 3. That's just the nature of weak acids or base. It's always going to be lower than the original chemical that is going to introduce it. Strong bases, remember that potassium hydroxide, if you put that in water, you're going to get 0.5 molar hydroxide. Calcium hydroxide, if you put that in water, you're going to get twice that concentration because of the fact that you have 2 hydroxide to deliver. On the other hand, weak bases like ammonia, you're going to generate less than if you introduce 0.5 molar ammonia, you're going to get less than 0.5 molar hydroxide. If you got bicarbonate, that's a weak base, then you're going to get less than 1.02 times 10 to the minus 3 molar hydroxide. You're always going to get less because they're weak. So some chemicals, remember I told you that some acids can deliver more than 1 hydrogen? Well, those chemicals are called polyprotic. Poly meaning many. Protic meaning protons. So polyprotic means that these chemicals have more than 1 hydrogen to deliver. Sulfuric acid's that way, H2SO4, phosphoric acid's that way, carbonic acid. And you can tell by the formula. Well, there's another class of chemical called amphoteric. Amphoteric are chemicals that in one instance will give up its hydrogen. In another instance, it's going to accept a hydrogen. So it's got a dual personality. A classic example of a chemical that's amphoteric is water. Look at the reaction here. Water here is going to accept a hydrogen from HCl. So water is the base in this reaction. HCl is the acid. So in this reaction, water is acting as a base. Then look at the reaction with water with ammonia. In this reaction, water delivers the hydrogen to the lone pair of ammonia. So in this reaction, water is the proton donor. Well, because water can, remember, it's not reacting with the same chemicals, reacting with different chemicals, but it has the capacity to either accept a hydrogen or deliver the hydrogen. Because it has that capacity, we call it amphoteric, meaning it can act as an acid or as a base, depending on the situation, depending on its partner. Another chemical is bicarbonate. This is bicarbonate, okay? This is bicarbonate. That's the name of that ion. In one instance, it can accept a hydrogen from water and becomes carbonic acid, and in the process generate hydroxide. So by accepting a hydrogen from water, it forms a basic solution. On another instant, it can deliver a hydrogen to ammonia, and by doing so, it is going to act as an acid. You get carbonate ion an ammonium in that particular case. So in this particular case, you're actually going to generate an acidic solution because this is this is donating a hydrogen to ammonia. So bicarbonate is also amphoteric. Here's another amphoteric substance. In this particular case, it's generally an acid in which the first hydrogen has been removed, and now the second hydrogen could be removed, or it can add the original hydrogen. So in this particular case, what you have is, oops, sorry. This is acting as a base. This is acting as an acid. So these are all examples of amphoteric substance. Likewise, H2PO4 can also be amphoteric. Okay, so make sure you recognize what chemicals could be amphoteric, because those are the chemicals that can act either as a proton donor or a proton acceptor. I'm going to try and get through this section so that the only thing that we need to do next time is to talk about buffer solutions. But this section really hits the heart of most of the calculations that you guys are going to be doing in acid-base chemistry. It starts with something called the autoionization of water. Water is the main chemical in any acid-base chemistry problem, and that's because water is a solvent. It's going to be the chemical in most abundant. Okay. Now, autoionization means that water will break up to hydrogen plus and OH minus. So it just instantly does it. If you have a beaker full of water or a cup full of water, 2 in 1 billion water molecules, 2 in 1 billion water molecules is going to auto-ionize or self-ionize. And the self-ionization reaction is one water will donate its hydrogen to another water, and that water will become a hydroxide. And then the water molecule that accepts the hydrogen ion becomes the hydronium. That's what we mean by auto-ionization or self-ionization. Water basically plays with its partner and delivers the hydrogen to a partner. And by doing that, it becomes hydroxide and hydronium. But notice that you can't get the hydronium without forming a hydroxide. So in the solution, you actually have equal amount of hydronium and hydroxide. And you can't stop this. Water just naturally does this. Okay, water just naturally does this. It auto-ionizes 2 in 1 billion. Because 2 in 1 billion does this reaction, what do you think the K equilibrium should be for this particular reaction? Do you think it's very efficient, or do you think it's very inefficient? If you say that it's very inefficient because only 2 in 1 billion does this, then you're right. And the K, we call this Kw because it's the reaction of water, is so small that that equilibrium constant is 1 times 10 to the minus 1 times 10 to the minus 14. That's a very, very small number. Okay. And that's because only 2 in 1 billion does this reaction, autoionization. But remember, when you have a cup of water or a beaker of water, that represents moles and moles and moles of water molecules. That's 10 to the 23rd molecules. And so even though it's not a very efficient process, only 2 in 1 billion, when you're talking about moles and moles and moles of chemicals, there are sufficient amount to that will be in that solution, that will be in water. So what we have here is that Kw is the equilibrium process. Remember, the equilibrium value is the efficiency of that reaction, this reaction is not very efficient. So it's very small. If we do the math, okay, if we do the math, we can say that Kw is equal to the concentration of the hydronium times the concentration of the hydroxide. Just based on what we talked about in the previous slide. It's always the products of a reactant. And you might ask yourself, well, then shouldn't water be in the bottom of this equation? And the technical answer is correct. Water should be at the bottom of this equation because it's always the products, these are the products, over the reactant. But you only put chemicals in the mass action expression if those chemicals changes in concentration during the course of the reaction. Again, let me say that. You only put chemicals in this is called the mass action expression, only if the concentration changes during the course of the reaction. Now the hydrogen ion is going to change because that's going to have a certain amount of moles in the volume that it occupies. The hydroxide ion will change because that will have a certain number of moles in the solution that it's formed. But for water, if you have pure water, if you have a pure liquid, okay, if you change the volume or you change the amount of water in that particular liquid, let's say that I change it to a certain amount. Let me change my pen real quick. Okay, I add a certain amount of water. Remember that concentration is moles per unit volume. So if I add more water into my water, doesn't the mole increase? Doesn't the volume increase? In fact, what happens is that the mole increase at the same proportion as the volume. So the concentration of a liquid is constant, okay? You can also say the same thing in terms of a solid. If you have a solid and it has a certain moles because it has a certain chemical composition and it has a certain volume, if you have twice the amount of solid now, okay, that's a bad cube, but you get the idea. Doesn't the moles double and doesn't the volume double? So for a solid and a liquid, the concentration is always constant. That's why you never put a solid and a liquid in these mass action expression. So what you have here basically is the Kw, which is equal to 1 times 10 to the minus 14, is just equal to the aqueous phase in the chemical reaction, that's hydronium and hydroxide. And if these two are equal, then we can make that x squared, and that is equal to 1 times 10 to the minus 14. I apologize for introducing math to you guys here, but that's just the nature of chemistry. And if we solve for x, which is equal to hydronium and hydroxide, okay, which is equal to hydronium and hydroxide, the concentration that is. Remember I said that these two are going to be in equal amounts. Well, what is the square root of 1 times 10 to the minus 14? The square root of 1 times 10 to the minus 14 is 1 times 10 to the minus 7. So if you are at 25 degrees and you have pure water, the concentration of the hydronium is equal to the concentration of hydroxide. That's why it's neutral. And that concentration is 1 times 10 to the minus 7 molar. Okay? Now this number is intimidating to the general public. So what we do, scientists do, is we say, okay, let's make this number less intimidating to the general public. We're going to take, and the general public doesn't have to know this, but you do. Let's take the negative log of 1 times 10 to the minus 7. And if you take the negative log of 1 times 10 to the minus 7, guess what your answer will be? It will be 7. That's where we get the value of 7 for the pH of water. It has a value of 7 because the dissociation constant, or the Kw of water, is 1 times 10 to the minus 14. Because it has a Kw of 10 to the minus 14, then the hydronium, which equals the hydroxide, will have a concentration of 1 times 10 to the minus 7. But because we don't like 1 times 10 to the minus 7, we do a math function called the negative log, and we call that the pH value. Okay, we call that the pH value. And the pH value is nothing more than the power of hydrogen, because what we're doing is a power function. So if Kw wasn't 1 times 10 to the minus 14, let's say that we live in a different universe and the Kw is 1 times 10 to the minus 10. Okay, then what do you think the pH will be for that water solution at that universe? Well, we go back over here and we say, what's the square root of 1 times 10 to the minus 10? That would be 1 times 10 to the minus 5. And if we take the negative log of 1 times 10 to the minus 5, then that would be 5 right there. So the reason why we have water as 1 times 10 to, or a pH of 7, is because the Kw is 1 times 10 to the minus 14. And it's 1 times 10 to the minus 14 because only 2 in 1 billion water molecules autoionizes. Okay, so we're going to kind of, let me clear this up real quick, because the Kw is not always 1 times 10 to the minus 14. Depending on the temperature, it can go up or it can go down. It's only 1 times 10 to the minus 14 at 25 degrees. If it was not 25 degrees, it was 50 degrees, then the hydronium ion concentration would be the square root of 5.48 times 10 minus 14. And then whatever that answer is, you take the negative log of that. Okay, so that's an important concept that we will use next time to calculate pH and pOH for different concentrations of acid. Okay, so next time it'll only probably take half an hour to finish this whole thing, and then we can go back into equilibrium. But again, this is a good breaking point, because the concepts that of why water has a pH of 7 really goes back to the chemistry. So I'm going to stop there. And if there's any questions, you guys can post it on the chat or email me. I saw that Ka is measured at a specific, yes, it's always measured at a specific temperature, because even though Ka is constant, that's why it's called the dissociation constant, that's why it's called the equilibrium constant. The way the Ka value changes is by changing the reaction entirely, in which case you have a new products over reactant to consider. But what will change the equilibrium constant, that's what Ka is, it's an equilibrium constant for acid, is varying the temperature. It's temperature dependent. So that's why we always have to specify what temperature we have, so we know that we're using the correct Ka. So you're exactly right. It's for a specific temperature at 25 degrees, the Kw for water is 1 times 10 to the minus 14. For an acid, that's the value that you saw in that table, the Ka. That's the value they are at 25 degrees. If we change the temperature, those values would be invalid. Okay, that's true for any equilibrium constant. You're always citing the temperature. So that's a good question. Thanks, Barry. Um, Anything else? If not, I will meet some of you in lab. Chapter 14 is not as difficult as chapter 13. Chapter 13 actually sets up chapter 14, but there are just more concepts to kind of grasp. Okay, but if you understand solution chemistry, that's what we are doing in chapter 14, but now we're doing it in the context of some chemical reactions. So chapter 14 is an extension of chapter 13, but now we're looking at specific chemical processes. Okay, and the bulk of the calculations that you guys are going to be doing in chapter 14, we will be covering next time. That is pH and hydronium ion concentration. That's what we will be talking about next time. Okay, if you go on to med school, you want to know your acid-base chemistry because there are a lot of acid-base chemistry in your MCATs. The autoionization of water simply means that water will act as an acid and a base in, say, a glass of water. And the reason why it has a pH of 7 is because that equilibrium has a value of 1 times 10 to the minus 14. And so when you solve for the hydronium ion concentration and the hydroxide ion concentration, first of all, they're going to be equal because the solution is neutral. You don't have an excess of hydronium or hydroxide. In fact, let that be your definition of neutrality, that there are equal amounts of hydronium and hydroxide. Do not define neutrality as pH 7, because if the equilibrium constant is different, then when hydronium and hydroxide are equal, the pH doesn't equal to 7. And today you're going to see how to calculate pH as well. You're going to have to learn how to use the log function in your calculator and 10 to the x, which is the anti-log function. So we'll do that shortly here. In the meantime, what you should know is that when we have water autoionizing, then this is the equation that you need to solve, where this value right here is the equilibrium constant, basically the efficiency by which water reacts with itself. And you can see that it's a very small number. So that means not very much of the reactant converts over to product. Remember that K equilibrium, in this case Kw, is an indicator of efficiency. We saw Ka when we talked about acid-base chemistry, and we had Kb. And for weak acids and weak base, these things were much, much smaller than 1. They had negative exponent. These things can never be negative, but they can be very, very small. As small as like 10 to the minus 30th or 10 to the minus 90th. So it's very, very small. Anyway, what you will be able to do in this particular case is do the math. You guys are going to see this in Chem 201, so don't worry too much about the mathematics here. Just know how to use the equation. Okay. What you will see is that when you solve for the math, the hydronium and hydroxide, because they are equal to each other, is going to be written as x squared equals 1 times 10 to the minus 14. And so if you solve for x in this case, you get 1 times 10 to the minus 7. That's just the math. Okay. And because we don't like values that have exponent, 1 times 10 to the minus 7, 1 times 10 to the minus 14, even 1 times 10 to the minus 2, what we do is we use a function. And remember what a function is. It's just a mathematical operation. If you take the square root um, of something, then what you will see is that that's a function. You just see something. Let me just see what's going on here. Hold on. Yeah, this thing should be. Thanks for letting me know about that. I moved it out of the way. That's the. All right. Thanks, Sally, for letting me know about that. Anyway, what you will see here is that when you have an exponent, you can do a function called a power function. And a power function just means that you're doing 10 to the x or log base 10. Okay. And what we can do is we can take an exponent and make it a whole number or make it a number that you could be comfortable with. And so that's what we call the p scale. P means power, and it's the negative log of a exponent. So what we can do is we can take a hydronium ion concentration, say 10 to the minus 7. And if we take that number and we say um, log of 1 times 10 to the minus 7, and then we take that answer and we take the negative of that answer, what we get is the pH of that hydronium concentration. Okay, so what you need to do is you need to take a concentration, take the log base 10 in your calculator. That means that you guys are going to have to learn how to use your calculator and take the negative of that answer. And I'll show you how that works shortly here. Okay, um, so that is your P function. That is your P function. And then the anti is taking the pH value and raising it to the 10th power, but making sure that the pH is the negative. And that'll get you the original concentration. So you can do that for hydroxide as well. And you can do that for any equilibrium constant, because equilibrium constants, remember, are very small, at least for acid-base chemistry. So let's take a look at some examples. Let's take water. And water, if you write it longhand, is 6 zeros and then a 1. And it's 1 times 10 to the minus 1. And let's see how we can do this calculation with our calculator. Whenever you have a nice clean number like 1 times 10 to the minus 8, 1 times 10 to the minus 9, 1 times 10 to the minus 3, then you can easily do this in your head, because if you take the log function of that, that's just 8, that's just 9, that's just 3. So you can see that 1 times 10 to the minus 7, that's just 7. And that's because this is a nice clean number. It's a 1 to the exponent minus 7. And so when you take the log of minus 7, you get negative 7. And the negative of negative 7 is just 7. Okay? But if you don't have a nice clean number, suppose you have a number of 1.67 times 10 to the minus 5. Well, you need your calculator. And let me show you how that's done. Here, let me just show you that in your the calculator real quick. Let me share that. So this is a calculator, and what I'm going to do is clear it, and you guys probably have a calculator that you can do. And what I'm going to do is I'm going to put 1.67, and I'm going to use this key to get the exponent. Okay, you guys should have a double E or an EX function in your calculator, and that's to get it in scientific notation. And you guys did this back in chapters 8 when you worked with the moles. So that's not new. What I'm going to do here is do change the sign, and there's a change of sign right here, and I'm going to put 5. So that's 1.67 times 10 to the minus 5. In fact, when you work a problem in Canvas, Whenever you want to use times 10 to the exponent, use E. It's much cleaner and easier that way. That way you don't have to worry about superscript. Anyway, what we're going to do is we're going to take the log of that. So I'm just going to hit this. This is a log base 10. And when I do that, you see it's a negative 4.78. I need to make that the negative. So that right there is the pH of 1.67 times 10 to the minus 5. You notice the exponent's minus 5. So your answer is going to hover somewhere between 4 and 5. Okay, because the magnitude of the number when you do the log is based on the exponent. So if you have a number like 14.78, you know you're way off and you messed up on your calculator. But somewhere like something like 1.67 times 10 to the minus 8, well, that's going to get you somewhere between 7 and 8 in terms of the value that you have. So let's do the inverse. Let me change screen here real quick and then show you this so you guys can see this. And then I'll show you the inverse calculation. So this is what we have. And you can see that written longhand, I get 4.777. That's if you do not round off your numbers, okay? You need to round off your numbers to the correct number of significant figures. And right now, if you look at this concentration, there are 3 sig figs there, okay? When you do a log function, the significant figures are after the decimal point. So 3 sig figs in your value means that you have to have 3 digits past the decimal point. That'll give you 3 significant figures because this 4 right here is a reflection of that exponent. That tells you the magnitude. So whenever you're doing pH calculation, look at the concentration, count the number of significant figures, and then that's how many digits you should have at the end of your decimal point. Now, if you take a look at these values right here, 1 times 10 to the minus 8, that's only one significant figure. So this really should be read as 8.0. This should be 9.0. This should be 3.0. Because the digits after the decimal tells you the number of significant figures. And yes, it's 0, but that's still significant. Okay. So let me go ahead and clear this. And then that's the sequence that we did. Okay. And what we're going to do now is do the inverse. Let's say if we can't take 4.77 and pull out 1.67 times 10 to the minus 5. So I'm going to switch screen on you again. Okay. Here's the calculator. And in the calculators, if you have a calculator, it's actually a way to change the number of decimal point that you have. And you can see right now that I'm pulling the number of decimals. So what I'm going to do is I'm just going to say there's 3 decimal. That way I have 3 digits after. So what we're going to do next is I'm going to change the sign here. And then I'm going to use this function, 10 to the x. And look what happens. I have 1.67 times 10 to the minus 5, which was what my hydronium ion concentration is. So practice this. I believe you guys have some homework problems that deal with calculations because you'll see a lot of problems in acid-base chemistry that will require you to change concentrations to pH and pH to concentrations. And that's an important skill that you will need whenever you do acid-base chemistry. Okay, so let me go ahead and switch screens. And let's move on. Okay, so this just tells you the rounding off rules, which I told you. Okay, these are the steps that you would follow in order to calculate pH. Enter the hydronium, click on the log key, and then change the sign. That's what we did in the previous problem. And then write your answer with the correct number of significant figures based on the concentration. The reverse way is Some calculators, you have to hit 10 to the x first. Other calculators, you have to put in your numbers first. It depends on your calculator. I don't know what calculator you have, but depending on your calculator, you'll know when you do this because it'll give you some error. But what you will do is you will hit log 10 to the x and then you put your negative pH, or you put your negative pH and then you hit your log or your 10 to the x key. Okay, so the yellow and the white are for two different versions of calculators, and then you get your answer. So, what you will find out when we do these calculations is that when the hydronium ion concentration is higher than the hydroxide, because there's always a balance. When one goes up, the other goes down because of the fact that hydronium times hydroxide equals 1 times 10 to the minus 14. So when one goes up, the other one has to go down. Or when this one goes down, the other one has to go up. There's always a balance there in terms of the concentration. So when hydronium is higher than hydroxide, you have an acidic solution. This is acidic. When hydroxide is greater than the hydronium, then it's basic, because the hydroxide dominates the mixture. And that when they're equal, you have a neutral solution. That's why I said make sure you define neutrality as hydronium and hydroxide being equal, and not so much that the pH is 7, because the pH being 7 is only because your Kw is 1 times 10 to the minus 14. If your Kw was 1 times 10 to the minus 16, guess what your pH would be at neutrality? It would be 8. Okay, so let me clear this real quick, and then you can see exactly what I was talking about here. Okay, hydronium and hydroxide. If you take the negative log of all of these, you get an amazing equation. pKw, which when you have 1 times 10 to the minus 14 is 14, okay, is equal to the pH plus the pOH. So we know that at neutrality, when KW's 1 times 10 to the minus 14, this is 7. This is also 7. Guess what? 7 plus 7 equals 14, which is that. So you know that if your pH is 1, your pOH has to be 13, because the 1 plus 13 equals 14. What we are assuming now is that we're assuming we're at 25 degrees, so that KW equals 1 times 10 to the minus 14. You need to make that assumption unless otherwise stated, okay? For the most part, we can make that assumption for almost every problem, except when you get to General Chemistry 201. Then we'll change the temperature on you. But for your class, you can assume that we're talking about a 1 times 10 to the minus 14, 25 degrees, unless otherwise stated. And it'll tell you, use this KW, okay? So this is a really handy equation, because then you don't have to worry about multiplying. All you got to do is add. It's much easier to add than multiply, okay? So what you see here is the relationship that between hydronium and hydroxide. So again, when this dominates, you have an acidic solution. When this dominates, you have a basic solution. When they're equal, it's neutral. There's a there's this relationship that I just talked to you guys about. Whenever your hydronium ion concentration is 1 molar is actually 1 times 10 to the 0. Okay, because anything to the exponent 0 is just 1. That's just a mathematical operation. So when you have 1 times 10 to the 0, guess what your pH is? It's 0. Yes, you can have the 0 pH. It means that your acid is 1 molar. You can actually get negative pH, because if you get negative pH, that means that your concentration is higher than 1 molar. Okay, but for the most part, we have concentrations of 1 molar or less. That's what you guys will be working with in today's lab. Okay, so but look at the relationship. 0 plus 14 equals 14. There's always a balance there. There's always a balance there. And so here we have neutrality for 25 degrees. 7 plus 7 is 14. And then all the values in between. You can see that when the pH gets smaller, it becomes more acidic, but that means that the pOH gets higher. Okay? A smaller pH means more hydronium. Okay, so please remember that, because that's, you always get mixed up, especially when there's a exam question there. When the pH gets smaller, you have a more acidic solution. It means that you have more hydronium. On the other hand, when the pOH gets bigger, you also have a more acidic solution. Okay, notice when the pOH gets bigger, you also have a more acidic solution. When the pOH gets smaller, you have a more basic solution. Your pH gets larger. And if we're talking about 1 times 10 to the minus 14 as your Kw, your range is generally between 14 and 0. Of course, if you have concentrations of hydronium that are bigger than 1.0 molar, then you will get negative pH, which means that your pOH is going to be higher than 14. Okay, because the two added together will always be equal to 14 if Kw is 1 times 10 to the minus 14. So please remember that. This table looks pretty simplistic, but there's a lot of questions that could be asked based on the concepts of acid-base chemistry. So what we have here is we basically have that. So here's a question. What is the pH of potassium hydroxide with a molar of 3 times 10 to the minus 4? So this is potassium hydroxide. Okay, I want to make sure that you understand what this question is asking, because potassium hydroxide is a base, and yet we're asking for the pH. The way you would solve this problem is, first of all, recognize that potassium hydroxide is a very strong base. That means it is a strong electrolyte. If you don't recognize that potassium hydroxide is a strong base, go back to the previous section where I identify the 7 strong acids and the strong bases. Anything with a group 1 metal and hydroxides are strong base, which means that the concentration of this being 3.0 times 10 to the minus 4 molar gives you an equal amount of hydroxide of 3.0 times 10 to the minus 4 molar. Okay, that's just the nature of strong acids and strong base. The concentration of the chemical is equal to the hydroxide or the acid if you have an acid. So in this particular case, what I can say right away in this problem is that my hydroxide ion concentration is 3.0 times 10 to the minus 4. That's what I can say. And the reason why I can say that is because this is a strong base. You cannot say that if you have a weak base or a weak acid. That's not true. But if you have a strong, that means it dissociates 100% of the time. The concentration of the chemical that you have is equal to the hydroxide ion concentration. Well, take the negative log of this, and what you will see is the following. Let me just show you that in my calculator so that you guys can see that worked out. Okay. So this is 3 times 10 to the minus 4 is not a number you can do off the top of your head. If it was 1 times 10 to the minus 4, then the POH would be 4. Okay, but it's 3 times 10 to the minus 4. So that's what I'm going to do, put here. 3 exponent 4 negative. And what I'm going to do is I recognize 3.0 times 10 to the minus 4 has 2 significant figures. I'll worry about that when I get the pH value. I'm going to do the log function, and then I'm taking the negative of that. So 2 significant figures will make this 3.52. So let me go back and show you my screen. Okay, so this right here is POH, that's 3.52. Then to calculate the pH, remember the pH plus the POH equals 14. So if I just subtract 3.52 from 14, I would get my pH value. That's the way I would solve this problem, okay? Because the question is asking what is the pH. It's not asking for the POH, it's asking for the pH. So if I take my handheld calculator and subtract 3.52 from 14, I get 10.48. So that would be my answer for this problem. Make sure you know how to do these because you'll see a whole bunch of questions like this in the homework as well as this coming weekend. Okay, so let me just do this real quick and let me clear this so that you guys can see. There it is, 3.52, because your this is your POH, and then your pH is going to be 10.48, like I said. Much easier route than you could have also gotten this answer. You could have also gotten this answer, pH, if you did this. 1 times 10 to the minus 14 divided by 3 times 10 to the minus 8. That'll be your hydronium ion concentration. Sorry, not 3 times 10 to the minus 8, 3 times 10 to the minus 4. 1 times 10 to the minus 14 divided by 3.0 times 10 to the minus 4. That's your hydronium ion concentration. You can just take that answer and take the negative log of that answer, and you would get this same thing. So there's 2 ways to get to your answer given the hydroxide ion concentration. And again, that's what you will see in a routine basis. This is a different question. It says, what if you're given a hydroxide, what is the pH? And I won't go through this exercise because it's worked out for you here. Okay, what I do want to show you real quickly is this relationship. This is a relationship that I kind of created this. This is a handy equation or chart to use, because given any one of these, hydronium, hydroxide, pH or POH, you can calculate the other 3 as long as you know Kw. The other information you need is Kw. So remember that the relationship between hydronium and hydroxide is that hydronium times hydroxide is Kw. So if you have hydroxide and you take Kw and divide it by hydroxide, that'll give you hydronium. If you got hydronium and you take Kw divided by hydronium, that'll get you the hydroxide. So basically, you have a relationship here that gives you hydronium and hydroxide. You also have a relationship here in which the pH plus the POH equals pKw. Okay, that's what you see right here. Now, how do you go from here to here? That's your log function. That's your power function. Let me clear this real quick. And that's what you see. Okay, and that's what you see right there. So remember our KOH problem we started with here? Well, the route that I took when I did this example was I calculated POH and then I calculated the pH. But you could have easily calculated the hydronium because you know KW and then calculate the pH. Either way, you can calculate the other three given any one of these. So you guys should practice this because again, those are common type of calculations that you do in acid-base chemistry. Okay, so here are just sample questions and you guys should take a look at and see that. Don't really have time to dwell on that um, because I want to make sure that I cover the entire section and start covering at equilibrium. But in terms of why is acid-base chemistry so important? It's important because if you become a doctor, like I said, a lot of the chemical reactions that takes place in your body is governed by the pH of your blood. Okay. Another thing is that if you have environmental concerns, and who doesn't have environmental concerns these days with the COVID-19? But in terms of pollutions and chemicals that we emit into our atmosphere, uh, the rainwater is actually not 7. Rain coming from the sky doesn't have a pH of 7. And the reason why it doesn't have a pH of 7, and that's okay, is because when rain falls from the sky, it will absorb the carbon dioxide from the air. When it absorbs carbon dioxide from the air, it naturally reacts with that and form carbonic acid. So rainwater is actually is actually um, acidic because part of it has carbonic acid. Okay, um, and carbonic acid will ionize and will give you hydronium ions. Let's take a look at what happens when we have pollution in the air. If we have pollution like sulfur dioxide, and that's why we don't burn coal these days, but back in the 60s and 70s, we did burn coal. And the problem with coal is that it has a lot of sulfur in it. Coal is nothing more than the remnants of whole rainforests. When trees die out or rainforest dies out and it's compact, that organic matter turns into coal. Petroleum is actually when dinosaurs that dies out and it's compact with high pressure. Then the dinosaur remains turns to petroleum. But coal comes from rainforests and the decay of that. Because proteins have sulfur in them, coal also has a high concentration of sulfur in it. And what happens is that um, when you burn coal, you also release the sulfur. And guess what happens when the sulfur gets into the air? It converts to sulfur dioxide, and then when it emits into our atmosphere, it reacts with the oxygen in our air, and then it forms sulfur trioxide. And why is that important? Because when rain comes down and there's sulfur trioxide in the air, you get battery acid raining down, raindrops of battery acid coming down. And that's why we eliminated burning coal, or at least we cleaned it up, because they actually recorded rain in Wheeling, West Virginia. West Virginia is a great mining state, but they actually recorded the rain coming down in Wheeling, West Virginia with a pH of I think it was 2.79. That was really, really acidic. Okay, so that's why coal is expensive, because we have to scrub out the sulfur. Of course, we don't live in the East Coast. We live here in Southern California, where we like to drive cars. Well, why do you think we have smog tests? The reason why we have smog tests is because when we burn air to combust our gasoline, air has a high percentage of nitrogen. Well, when nitrogen goes into our engine and it reacts with oxygen, we form nitrogen dioxide. Nitrogen dioxide, if it's released into the atmosphere, will react with water to form nitric acid and nitrous acid. That's not very good. Okay, so if you ever are, if you lived in LA or Pasadena or San Bernardino in the 80s, 90s, and even probably today, and you see that brown haze above you and it starts to rain, take shelter. Nitric acid is coming down. Okay, so that's why we're concerned about these things and its environmental impact. Nitric acid is coming down, and so if we smog our cars, we don't release nitrogen dioxide, and then we don't get that brown haze above our city, and then we don't get rained upon with nitric acid. So here's the effects of acid rain. This is my friend George back in 1944. He's in Washington um, Square Park. And this is him back in 1994. He's caught leprosy. And the reason why this happens is because marble statues are nothing more than calcium carbonate. Calcium carbonate is the same material that chalk is made of. If you ever take a piece of chalk and put it in vinegar, it'll dissolve. So imagine years and years. In fact, how many years is that? About 50 years of rain coming down, and the rain being acidic, especially back east. It'll start wearing away at the marble. And that's what you see in terms of whole rainforests being dead. And so they've passed environmental laws to prohibit the emission of these chemicals because they certainly ruin our environment. Okay. So if you ever plan to be an environmental scientist, these are things that you study. In terms of pH values, know that generally pure water at 25 degrees has a pH of 7. But seawater, baking soda, saliva, ammonia, bleach, and liquid Drano are all basic. On the other hand, vinegar, your soda, rain, acid rain, um, battery acids, even the gastric juices in your stomach are acidic. In fact, your stomach has a pH of 1. It's very acidic. Okay, that's why if you ever get an ulcer and you start burning through your stomach lining, it's really upsetting. Or if you have acid reflux, it has a burning sensation because that's a pH of 1 that's coming through. Not very good. The last topic I want to cover is buffers. Buffers are important chemicals because these are chemicals that if it's contaminated with acids or base, they resist pH change. That's why it's called a buffer. A buffer is basically something that compresses or resists changes. And so the reason why it's important is because our blood is buffered at 7.35 to 7.45. Okay? If it gets below that, we have a terminology called acidosis. If it gets above that, then we get a health ailment called alkalosis. Acidosis and alkalosis. So for those of you who want to go into the nursing field, those are very important concerns. How does our blood, what are the buffer systems in our blood? The proteins in our system, the phosphates in our system. Remember that DNA has a phosphate backbone, and so there's a lot of phosphates in our body, but most importantly, it's the carbonic acid bicarbonate equilibrium that is responsible for buffering our blood. In fact, these two exists in a ratio of 10 to 1. And the chemistry is the following. We have, this is called bicarbonate, this is carbonic acid. If we have excess acid, remember that pH is equal to the negative log of the hydronium ion concentration. This is an important equation because the only way your pH will change is if the hydronium in your system is high or low. But what happens if we remove the hydronium or the hydroxide in your system? Well, that means that the pH doesn't change. And that's exactly what a buffer does. What a buffer does is that it takes the hydronium and it reacts with it so that it converts it over to, yes, this is an acid, but it's not hydronium. Carbonic acid is an acid, but it's not hydronium. Therefore, it's not going to lead to a pH change. Okay? And that's the key to a buffer. It removes hydronium and hydroxide, which are directly influenced to the pH and the pOH. So by converting it to another chemical, your pH does not change. Okay, so that's what you want to see. Buffers are weak acids and weak base and their conjugates, exactly. Okay, they have to be conjugate pairs. That's why we talked about conjugate pairs in the beginning. Anyway, let me just show you some chemistry here. So what happens if we have too much carbonic acid builds up because it's removing the acid in our system? Well, there's a neat way of removing that carbonic acid buildup. That way it doesn't reverse on you. If this reaction build up and there was no exit, it'll reverse on you and then you just increase your hydronium. But what we do is we basically breathe it out and sweat it out. So any carbonic acid build up in us, we breathe it out so we have carbon dioxide and we sweat it out. That way there's no excess carbonic acid in our system. That's the chemistry. How does hydroxide not change? Well, the hydroxide doesn't react with bicarbonate. It reacts with carbonic acid, and then it forms carbonate, bicarbonate, and water. Again, you are removing the main culprit in changing pH, hydronium and hydroxide. That's how buffer system works. And it's important because when you have acidosis, the symptoms are depression of the acute nervous system. You basically will have fainting spell. You might go into coma. Eventually, yes, you will die. Okay, you will die if you have acidosis. And what are the causes? Well, you have a difficulty breathing, so therefore you have difficulty removing that carbonic acid, so it reverses on you and produces more hydronium. And that's maybe because of pneumonia, asthma, anything that diminish carbon dioxide from leaving your body. What is the mechanism? Well, the carbon dioxide doesn't leave your lungs, and so there's a buildup of carbonic acid. That's the respiratory. The metabolic basically means that you start starving yourself or you do heavy exercise. When you starve yourself, then you start using fatty acids, so that increases the acid in your system. Or heavy exercise, you produce a lot of lactic acid. So when you do that, your body basically sees a big surge of acid, and if it can't handle it, then your pH will drop. Okay. Let's take a look at the flip side. Alkalosis as well will cause muscle cramps, convulsion, and death. And what are the causes? Remember that you are removing hydronium, you are increasing hydroxide. So if you have heavy breathing and so you expel more carbonic acid than usual, then it's going to grab any hydronium acid in your body and convert it over to carbonic acid. That's not good. This is because you are breathing heavily, because you are hysteric, or maybe you have a fever, or maybe you have a reaction to a blood. Usually when someone hyperventilates, you give them a paper bag So they breathe into the paper bag. And the reason why they need to breathe in a paper bag is because they need to recycle the carbon dioxide that they just breathed out. And by doing that, you reverse the reaction that I showed you earlier. So you don't want excess loss of carbon dioxide. And what are the metabolic causes? Well, you have a lot of acid in your stomach, and so if you have excess bulimia or vomiting, that certainly is going to cause um, a lack of acid in your system. So those are just some of the health concerns when the buffer system doesn't work in your body. And how exactly does the buffer system work? Remember, there's a conjugate here, and any excess acid that you add converts over to another chemical and therefore removes the hydronium. That's the key. If you have excess base, then that reacts with the hydrogen ion of the acid in the buffer system, and that forms water. Again, you're removing hydroxide. That's the key. So a buffer system works on the principle that it's removing hydronium or hydroxide. Therefore, it's not affecting the pH or the pOH. That's the key. So this is just more or less the same in a chemical reaction of what's going on. So you guys can look at that. There's this equation that you guys should know how to use, and that's how to calculate the pH from a buffer system. Suppose I have a buffer system in which I have carbonic acid, H2CO3, and bicarbonate, and I know this concentration. Well, what we need to do first is we need to figure out what the Ka is for carbonic acid and convert that to the pKa, because that's the first part of this equation. Then we need to know the concentration of the acid and the concentration of its conjugate. And if we have that, we can plug it into this equation right here and then calculate the pH of that buffer. If you guys ever go to a biology lab or you work in a clinical lab, you're going to find out that your assays, these are the chemicals that you're dealing with, has to be buffered. And in order to prepare a buffer solution, you got to be able to use this equation. It's called the Henderson-Hasselbalch equation. You don't have to derive it, just make sure you know how to use it. So that's what I'm illustrating here, how to use this equation. HA and A minus are the conjugate pairs, and you just have to figure out what the concentrations are, and then you need to figure out, based on the Ka of the acid, what the pKa is, and then you can calculate it. You can either calculate the pH or the pOH, depending on your buffer system. So let's take a look at this example. This will be the last example that I do. And this one's pretty straightforward. We have bicarbonate, it's 0.100 molar. We have carbonic acid, that's 0.200 molar. So I give you those concentrations. You don't have to figure those out. I give you the Ka, 4.3 times 10 to the minus 7. That's your Ka. So you have to calculate the pKa. And remember, that means that you have to take the negative log of that number. So if you have a calculator, go ahead and punch in 4.3 to the exponent 7 negative, and then take the log of that. And if you do, what you will see is that that comes out to 6.37. So all we have to do now is stick it into this equation. pH equals pKa plus the log of the base over the acid. The base is 0.1, the acid's 0.2, and pKa is 6.37. What is the pH of this buffer solution? 6.37 plus the log of 0.1 over 0.2. Let's do this function first. 0.1 divided by 0.2 is just 0.5 and take the log of that, base 10, that comes out to negative 3.301. And if we add that to 6.37, what we get is pH value of 6.07. It says 6.06897, but we're just rounding it off to 2 digits after the decimal because we're using two significant figures right here, two significant figures right there. So let's take a look at the workup now that I showed you the calculations. Let me clear this. Here it is right here. Okay, we plug it in, we get 6.07, just like we calculated. So these are good examples to follow, and we're pretty much done with that. Okay, pretty much done. So the main topics that I covered in this discussion was how to calculate pH, pOH, hydronium, hydroxide. You need to know how to do that. We covered alkalosis, acidosis, and buffers. And then in terms of some conceptual, acid rain. So you will see more of this, not so much in Chem 200, but in Chem 201. In fact, we just finished in my Chem 201 class, we had a big old test on acid-base chemistry. And it's much more involved than the 2 lectures that I just gave you. It actually covers like 2 chapters, which covers practically 3 weeks. So, but this is a good start. These are the fundamentals that you guys will need. Okay. So I'm looking at the chat. Let's see. Yeah, if you do acid-base chemistry, you'll see that a lot of those things are just all right. Thanks. Okay, just practice those problems. I need to switch gears so that I can cover some kinetics.